I'm now going to show a second example of how we deal with something constantly changing as a function of time. In this case, I'm going to assume we've got some bunch of radioactive isotope atoms, large numbers of atoms, and that each atom has a probability P of decaying into something else per unit time. So P per unit time. So these, for example, might be carbon-13, and they have a chance of decaying into carbon-12, or any other radioactive isotope. Now this is a problem you've probably seen before at school and know the answer to, but what we're going to do is talk you through how you approach it from the differential equation point of view. The benefit of doing it this way is we can allow for more complicated situations. For example, when you have atoms that decay into a particle which is itself radioactive and then decays into yet another particle, or which has a 30% chance of decaying one way and a 70% chance of decaying another way, because we can handle all that. Anyway, first step, think about the physics. So what's going on here? So for each atom there's a probability P per unit time that it'll decay. And so, as time goes on, there are going to be fewer and fewer atoms. We can think about it graphically. So we're going to have the number of radioactive atoms, and that's going to start at some high value. It's going to go down. It's never going to go up. Is it just going to keep going down straight? Well, the slope here is telling you how many atoms are decaying per unit time. It's d number by d time. And what's that going to depend on? Well, the number of atoms decaying per second is going to depend on the number of atoms you have to start off with times p. It's going to be n times p. So that means that when there are lots of atoms, there are going to be lots of decays. It's going to drop fast. But by the time there are only a few atoms left, there are going to be fewer and fewer decays. So in fact, the curve is going to flatten out, look something like this. To begin with, there are lots of radioactive atoms, and so a good number of them are going to be decaying. As time goes on, the probability of a given atom decaying is exactly the same, but because there are fewer atoms, there's going to be less decay, so it's going to flatten out. So we'd expect to have a graph that looks something like that. If we don't, we've done something wrong, most likely. Okay, can we come up with a quick estimate of how long it's taking to go away? Well, roughly speaking, the time needed to get rid of these atoms is going to be, roughly speaking, 1 over the probability. So if there's a 1 in 10 chance of an atom decaying per second, then it would take roughly 10 seconds to get rid of all of them. Not quite all of them. That would be assuming the rate of decay remains constant, so that's this time here. In practice, it'll take a bit longer than that, but this gives us a rough estimate of the time for a pretty hefty fraction of the atoms to have gone away.